Now that we've had a chance to do dt convolution, it's time to turn to the continuous time case. Now in the continuous time case, we're going to have a lot of the same structure. The output is going to be the CT convolution of the input and something called the impulse response. And so we basically just have to see how these arguments differ from the graphical ones we presented for discrete time. Here we have a more algebraic proof. So for this starter, we just want to see why the output of an LTI system is the convolution of the input with the impulse response. This very important fact about LTI systems. So for discrete time LTI systems, we saw that the output was the discrete convolution of the input and something we called the impulse response. The impulse response was the output of the system to the input delta of n, the Kronecker delta function. Here we're going to look at the impulse response as the output of the CT LTI system when the input is the Dirac delta function. So we can define this as the convolution, so this is the definition of convolution. But we want to be able to show that in fact the output of the LTI system is in fact the convolution of the input with the impulse response. So remember, the impulse response is just going to be delta of t goes into my system h, and I'm going to get back out h of t. And so we want to use the linear and time invariant properties to show that in fact this convolution is going to give us the output signal. So we have our system here. Our impulse response is the output of our system with input delta of t. So we can write that down. Okay, so let's write this down. Delta of t goes to h of t when I apply the system h. Well, the system is time invariant, and so that means that if I delay the input, then I delay the output by the same amount. So let's delay this delta of t. So this is a delay, and I get the same delay at the output. So I get delta of t minus tau goes to h of t minus tau. I've delayed it by tau. Okay, so now I can multiply by a constant, and I can use linearity to show that if I multiply my delta of t minus tau, which is a function of t, if I multiply it by a constant x of tau, then when I apply the system h again, I get just x of tau times h of t minus tau. Okay, so this is just using the linearity property. So now we've used both our properties, linearity and time invariance. So now we have to do a couple more tricks to get ourselves to show that the output of the LTI system is the convolution of the input with the impulse response. The first trick that we're going to do, or the main trick we're going to do, is we're going to now integrate this thing over tau. So we're going to integrate x of tau delta of t minus tau d tau, integrate it from minus infinity to infinity. Now, because integration is also a linear operation, it kind of acts like a sum, we can argue, and this is where I'm waving my hands a little bit mathematically, because you have to be a little bit careful here, but you get that the integral of x of tau delta of t minus tau is the integral of x of tau h of t minus tau h of t minus tau, the impulse response. So we're getting this is the discrete, this is the CT convolution. Now we have our identity from the previous slide, and now we just use the sifting property. If I integrate x of tau delta of t minus tau, I just pick up the value of x of tau at wherever this stuff in the middle of the delta is zero, where's the delta located, and on the tau axis it's located at t. So this whole integral here just becomes x of t. And this thing on the outside, we just leave it the same. So this shows that when I put in the system signal x of t into the system and I apply the system to it, I get the CT convolution. And so we have our theorem. If H is a CT LTI system with impulse response little h of t, then the output y of t to an input x of t is the CT convolution of x of t and little h of t. So this expression here, which is what we had above there. So what this means is that the impulse response actually, much like in the discrete case, contains everything you need to know about the system. The impulse response contains everything you need to know about the system. So, for example, to calculate the output of a system, you just need the input and the impulse response. Here's the input, here's the impulse response. And you just do an integral, and you get the output signal. Perhaps more interestingly, the system properties like stability and causality and so on are properties of the impulse response. And so this is sort of very important in a kind of sort of philosophical sort of way, because what we're doing is we're saying h of t is a signal, and so signal properties of h of t are equivalent to system properties of our system, H, our LTI system. So that is, we can look at the signal that is the impulse response, and we can say, oh, the signal looks like this. For example, h of t starts at 0, and then this will tell us, and we'll see this later on, that in fact the system is causal. So these kind of ways that we can look at the impulse response to determine system properties is very useful, because it sort of saves us all of the more abstract argumentation that we had to do when we were considering general systems. So now CT convolution satisfies many of the same properties as DT convolution, in fact most of them, maybe all of them. The first one, of course, is that it's commutative, so x star h is h star x, which means that when we're doing this calculation of the convolution, we can either flip h or we can flip x when we do the integral. So instead of doing a sum, we're going to be doing an integral. The other important fact, of course, is that it's associative. So for example, I could take x and I could apply h to it, h1 to it, so that's this, and then I could apply h2 to it, and that's equivalent to, say, first convolving h1 and h2, and then applying that total system to the signal x, and you get the same. The point is, you get the same output. So that's the associative property. This means actually, if I want to apply multiple systems in a row, which you do often in thinking about designing signal processing systems, for example, for communications or just DSP applications, you want to do A, then B, then C, but it turns out that you can do H1, H2, H3, or you can do them in any order you want, H3, H1, H2, or H2, H3, H1. All of these things are going to lead to the same output. So if we can apply them in any order, which order should we choose? That's a reasonable question to ask. And it might turn out that if you apply H1 first, you can build H2 more cheaply. And then H3, of course, is might be maybe cost the same. But if you did H2 first, you'd have to build a much more expensive H2. The implementation cost would be higher. So the cost is one issue. And we can think of cost as terms of money, of course, but we could also think of cost in terms of power or chip size or stuff like that. So power is also a major reason why we might want to do one of these systems first and then followed by the other. And then there's other issues like interference or other implementation issues, like you want to get rid of some high frequency artifacts because that'll mess up stuff later on. All these factors come into play when you're actually trying to implement these systems, but mathematically they're all the same. And so if you want to understand what the whole thing is doing, you can sort of mathematically, it might be easier to analyze it one way, but implementing it, you might analyze it a different way. So if our output of our system, we call it y of t, then we can compute it either using x star h or h star x. And the question is, maybe one of these is easier to compute algebraically than another one, but the thing to really look at is to interpret this formula. And so we can see this h of t minus tau, when we tried to prove this convolution, this is just a delayed copy of h of t. It's delayed by tau, and we multiply it by a weight, x of tau. So we can see that the output is a mixture of copies of the impulse response. But we can't use the sort of superposition trick like we do in discrete time, where we sort of just write out the impulse response and add it up. So basically we're going to get sort of two main approaches. The first is a graphical approach using our flip and slide, very similar, basically identical to the DT flip and slide, so hopefully it's a little more understandable after getting a dry run at it. And then the algebraic approach, where you just kind of manipulate integrals and just do some calculus, and hopefully the calculus is fairly straightforward and you get the output. So we're next going to look at these two different ways of computing the convolution, and in doing so we'll see how things are similar and different from the discrete time case.